Now we're going to talk about the Fourier cosine and sine transforms. They part from the Fourier integral representation of a given function f of x. We know that the Fourier integral is defined as follows: if w cosine of wx plus v w sine of wx, and this is times dw. And we know that a w is equal to 1 over pi from minus infinity to infinity of f of v cosine of wv dv, and v of w is equal to 1 over pi of the integral from minus pi to pi of f of v times sine wv dv. However, we know that all the even functions, if we consider a even function, we know that the Fourier integral will be equal to just the cosine component of the Fourier integral, having something like this. So that, yeah, having something like this, and we will also consider that a of w would be equal to 2 over pi from 0 to infinity of f of v cosine of wv dv. This is a even function. We have a different representation of a of w that was from minus infinity to infinity. However, as I was saying, as this is an even function, we can consider just half of the integral bounds from 0 to infinity and multiply it by 2, and we will obtain the same value of the integral here, considering again that this is a even function. So we can now set a of w to be equal to the square root of 2 over w multiplied by a new factor that will be equal to this. Then we will know that fcw will be equal to 2 over pi square root multiplied to 0 to pi of f of x cosine of wx vx. This is an a. So yeah, so we will have this representation now f of c, and also we can conclude that f of x will be equal to 2 over pi and square root multiplied by the integral from 0 to pi of fcw cosine of wx dw. So yeah, pretty much it. This is how we obtain the Fourier cosine transform, and it's given by this integral here. Similar to this, we can obtain the Fourier sine transformation, setting v of w equals to 2 over pi of fs of w. We can consider that fs of w will be equal to 2 over pi square root from 0 to infinity of f of x sine of w x dx, and that f of x will be equal to 2 over pi square root multiplied by the integral from 0 to pi of fs w sine of wx dw. And why is that? Well, as I was saying before, we know that the Fourier integral representation is equal to this, and that the coefficients v and aw are given by this integral. I mentioned before that we can change the value of the integral bounds and its coefficient because it was an even function, but it's more related to the fact that these are periodic functions. So as we know that they are periodic, we can just divide the integral by 2, and divide the integral from 0 to pi and multiply it by 2, and we will obtain the same result as considering the bounds of the integral from minus infinity to infinity. Another thing to consider is that the Fourier cosine transformation is only used for even function, and that this Fourier sine transformation is used for odd functions. So it is important. And yeah, this is how we obtain now the Fourier sine transformation of a given odd function.